Now, just to quickly repeat, what we found is that when we make the cut at an angle like this, then that resultant axial force that's generated on the inside. So now I'm drawing the left side. So this would be our P. And now there has to be only a resultant P that's going in this direction. Statics tells us that. But now what happens is when we break that force down, it's going to have one component this way, one component this way. So that is our N, that is our V. And I'm going to repeat what we just had on that earlier board. So we're going to have then that N is equal to P times the cosine of theta, and V is equal to P times the sine of theta. Now, notice all of those are less than P. The max it can be is P. In other words, what we know is that those have to be less than the magnitude. So less than P. I guess we should say or equal to. Because what happens when theta is equal to 0? Then the cosine of 0, cosine of theta is going to be equal to 1, and we get that N is equal to P. That's what we had earlier when we just cut it perpendicular. And then the sine of theta would be equal to 0. So there would be no shear on that plane. So now as soon as we make that incline cut, and again remember that this is our angle theta, now part of the load is resisted by normal and part of the load is resisted by shear. But now there's another thing that happens, and what happens is now this is the area of the cut. So the area of the cut that we have now grows. You can see that. A lot of cooking shows, cooking. If you're watching these, they'll say something like, cut your veggies, cut veg on a bias. That's a phrasing that's typically used, I think, Jacques and Julia and Gordon and all of those guys. They all say something like that. And what they mean is, if you have a carrot, that's my carrot, wow. Rather than chopping it this way, you're going to get that area. But if you slice it like this, then you're going to increase the amount of surface area. That increases the number of molecules then that's exposed to the hot skillet. It cooks at a different rate and so on. So we know that by cutting things on a bias like that, we're going to increase the area. So what our job to do then is to ask, well, what is that going to be? The way that we can get it is, and I'm going to redraw that cut, I'm going to call it like that. So remember, we've already got our distances. This was H, remember. Let me draw another sketch of that. There's our cross section. So H is the height, B was the width. And now we've got kind of this slanted plane like that. So that's the area of the cut that we have. So we had the base and then the height. So let's go ahead and call this length D for diagonal. And I'm going to rewrite again, that's our length theta. So area of the cut is the area over which those resultant forces are going to act. So we'd like to find out what that relationship is going to be. Now remember this value, that's just A. That is a cross-sectional area. It's a common engineering term. And to get that, that would just be B times H. So the area of the cut then, that's going to be the base width multiplied by that diagonal length. So everything hinges on what D is going to be. Now we can tell that by simple trig. We've got it kind of oriented differently than we normally draw when we first learned about trig in middle school. But now we can write out the relationship between D, H, and theta. So D, H, and theta. And if you want to, pause the video and see if you can figure out that on your own. It's not going to take you very long, especially if you just reorient it. So once you've had a chance to think about that, notice then that if you change the angle, then it's just going to be the adjacent side over the diagonal. So we know that H divided by D, that scalar is the cosine of theta. So that means then that D, if we rearrange this, we'll say that D then is going to be equal to H divided by the cosine of theta. And that means that D is growing. Remember, cosine is typically less than 1, less than or equal to 1. And we're going to then increase that area according to D. So I'm going to slide this up now, and let's now write the area of the cut. And that's going to equal to, I'll rewrite it, that's B times D, which is B times this guy, H divided by the cosine of theta. Well, BH is just the area. So that's going to be equal to A, the cross-sectional area, divided by the cosine of theta. And so now we have a relationship. I'm going to put a dash box around that. And the way that I use dash boxes in this class basically means that's a semi-important result. It's not going to be one that we're going to commit to memory, but it's one that's very useful that we're going to use in subsequent analysis. So we have that the area of the cut is equal to A divided by the cosine of the angle. So again, as we slice it, it grows. If a theta is very small, then cosine is very close to 1, but it's less than 1. And so we're dividing, say, by 0.95. And so we're going to get a little bit of an increase in the area. Then as we increase theta, we increase that cut of the area. Well, now we're ready to calculate what the stresses are going to be. So now we've got sigma is equal to, now remember, that's the total normal force divided by the cut area. So it's going to be N divided by the area of the cut. So N was equal to P times the cosine of theta, and then the area of the cut is equal to A divided by the cosine of theta. So if we multiply top and bottom by cosine of theta, that's going to give us P divided by A times the cosine squared of theta. So there's our relationship now for sigma. It's got the force, it's got the area of the cross section, and then it has the cut angle inside there. Now you've probably encountered this principle already in your undergraduate careers, and that is you don't like powers of theta. So it's considered kind of bad form. So frequently what happens is when we do this, we get rid of the square of the cosine. So this is a very common occurrence that we'll encounter, because, and another reason for doing that is it's a lot easier to visualize a theta, an angle, than it is the square. And so we can use the old double angle formula that we used back in the day. So let's recall, and I'll put that in quotes. Recall means you may or may not have seen this in your educational background, but we're going to pretend like you did so that we can just kind of keep moving. Now, my dad once told me he had to memorize 100 trig identities. This is back in like 1946 or something like that. So those days are over, man. But in any event, it's a good mental exercise, and hopefully you've remembered some of these. And it looks like this. The cosine squared of theta, hopefully you're going to remember this, is equal to, maybe you should try it on your own, it is equal to 1/2 times 1 plus the cosine of 2 theta. Remember that? The double angle formula. So double angle, that's a lot of times what it's shorthand. Double angle because you've got the double of the angle right there. And so we would write it then as sigma is equal to, now the 1/2 goes downstairs, so P divided by 2A, so that 2 is coming from this guy. And then we have 1 plus the cosine of 2 theta. Now I'm going to box that up like this. That's our final result. And normally when I do that, I want you to commit this to memory, but we're not going to memorize this one. So we'll say it is important. I'm going to abbreviate that. It is important, but you don't have to memorize. So don't memorize like one of those trig identities. It would be great to know, but there are so many other formulas in this class I need to ask you to commit to memory that when you don't have to, I don't want you to spend the mental space. So we're going to break this one down shortly, but before we do that, to close out kind of this part of this lecture and actually this lecture, let's now do the value for the shear stress. So that's going to be tau, and that's going to be, again, the total value of the shear force divided by the total cut area. So now that's going to be V times the sine of theta, all divided by, once again, A divided by cosine theta. So, I beg your pardon, that should be P sine theta. I'm just writing over that. It's not worth correcting. So we've got now P divided by A times sine theta cosine theta. Well, there is another product of trigonometric functions which we don't like. But again, if we recall back from our past history, we remember, I guess I said recall last time, remember this time, that the sine of 2 theta, there's the double angle, is equal to 2 times the sine theta cosine theta. So that means that this is equal to sine of 2 theta times 1/2. So this whole thing is equal to 1/2 times the sine of 2 theta. So now we have our final boxed formula for the shear stress. So now tau is going to be equal to P over 2A. There's that factor of 2 again, simply times the sine of 2 theta. And we'll box that one up. So once again, important, but you don't have to memorize it. Now let's sketch to close out what that means when we're doing something like this. If I draw the box like this and like this, oops, I'm sorry. Let me change that to, actually I am going to go ahead and erase that if I remember how to do that. Okay, then we're back to that. So now we've got this inclined plane like this, and then we've got it slanted like this. So now if on that back face we have P acting this way, then now I've got a bunch of little normal stresses coming out like this. That's our field of arrows going like so. And that exists all over the cut face. But now we also have acting a shear that's going parallel that looks something like this. So we've got a sigma field and a tau field. So now there are 2 fields of arrows. Or maybe we could say that there is a single field with 2 arrows on it, either one. But the important feature is that we have both a normal and a tau. And this is the first but not last time that we're going to see that. And that closes out our lecture for today.